Let's look at some different log functions that are not just in the form of log base b of x, but have some additional numbers being added or subtracted at the end, or a number being added and subtracting to x, what we're taking the log of. So in this first example, f of x, I've graphed y equals log base 2 of x plus 3, where we're adding the 3 to the x inside the parentheses, and we're taking log base 2 of x plus 3. I'm going to go through those same steps I did last time, where I do 2 to the y power is equal to x plus 3 to get an equation that I can then manipulate and solve. I went ahead and put it in x equals 2 to the y power minus 3, just so that I could make a table of values, plugging numbers in for y and figuring out x based on what I've plugged in for y. This allowed me to graph that function by hand. Doing so, I can compare that to my original parent function and see that log base 2 of the x plus 3, where I'm adding 3 inside the parentheses to the x, all that's done is slid the function to the left 3. I moved the function left 3 units. The shape of the curve, it still has that vertical asymptote, except that vertical asymptote has been moved left 3. I now cross the y-axis because I shifted the function left 3. So typically when I have a vertical asymptote of the y-intercept x equals 0, well, now I've shifted my function to the left, so moving the vertical asymptote to the left 3. How would we graph these in the calculator? So let's just compare that to another function, g of x equals log base 2 of x minus 5. So the difference here is the minus 5 is separate from the log base 2 of x. So we look at that as its own independent constant term. So if I were going to put this one into the calculator, I would need to have the log in base 10 form. So we can say that's the same thing as y equals log base 10 of x divided by log base 10 of 2, and then minus 5. Got to be sure you're putting that into the calculator with parentheses in the right place. So that's log of x divided by log of 2, close parentheses, and then we can subtract 5. So let's put that into the calculator. So we originally had a base of 2. So if we did log of x divided by log of 2, that's what the function looks like to start with. Now we have log base 2 of x minus 5 at the end. So we're going to do log of x divided by log of 2, and then put the constant minus 5. Now compare. And then our other one, just while we're here, was log base 2 of x plus 3. So now we have log of x plus 3 let me use my parentheses correctly, divided by log of 2. So let's compare. The curves all look very similar. The red one is our parent function, log base 2 of x, where we know 1, 0, 2, 1, 4, 2, 8, 3. What's happened is when we add 3 inside with x, it shifts to the left 3. When we subtracted 5 at the end with a constant, it shifted down 5. So this allows us to see that moving the function to the left with a horizontal transformation gave us the y-intercept, but that vertical transformation did not. And now we can look at any function and know what to expect. If I have y equals log base 5 of x minus 2 plus 3. Well, now I know this is the log base 5 of x function, but because there's a minus 2 inside the parentheses with x, it moved to the right 2. And because there's a constant in the place at the end where our vertical transformation is at, we know it moves up 3. So y equals log base b of x minus h plus k. H is our horizontal translation, plus h is going to be to the, if you see x plus h, that's how we know it's moving to the left. X minus h is to the right. And then the plus k value at the end, if we've got plus k, it's going up, and minus k, it's going down. And that's how we can apply those same transformations we've seen with any other function to logs as well.